Now that we have looked at some of the basic concepts in training artificial neural network, let's actually start training one. And for this course, we are going to use PyTorch for training, and there's also another Python package called TensorFlow which can be used, but I prefer PyTorch because it's more Python-like and a little bit easy to manipulate. Just like before, we would need to create the dataset and feature-wise the dataset and everything. And this is the process that goes into doing all of that. So at first, we'll clean up the dataset and feature-wise the dataset, split the dataset as we did before for classical machine learning models. But then what we would do is we would create a data loader, and that data loader helps us in training, and that will help us how to load data into the model so that we can calculate loss for each instance and then do the back propagation. And once we create a data loader, we can put that data loader into a model for training, and before putting that data into the model for training, we'll create the model itself. We'll say what architecture we need, how many number of hidden layers, number of neurons in a layer, and all of that would be decided while we create a model. We would define a loss function so that we can calculate the loss, and as I mentioned before, we are going to use an optimizer that looks at calculating the gradients and then updating the weights so that the model improves and is able to predict the values after a while. As the process is iterative, we would need to loop over the dataset again and again and again, and those loops for over the dataset are called epochs, and we would need multiple epochs so that the weights are optimized with the algorithm, the iterative algorithm that we use. Unlike the classical machine learning models where we just used the entire dataset, it's sometimes hard to use the entire dataset for training because there are a lot of weights that you need to optimize and a lot of gradients that you need to calculate. So what is done generally is the data loader splits the dataset into small batches, and for each of the batches you do the training, and once the training is done for one batch, it moves on to the next batch. So it's just splitting up the big data set into small chunks, and we train on small chunks, and this is just due to the limitation of memory that the model uses, and there are a lot of weights that need to be optimized. So we'll have a loop for batches for training part of the dataset, and we can use another loop for validation of the dataset on the batches. So within one batch of training, we will do a forward pass where we put in the inputs x1s, x2s that our featureizer gives us from the dataset, and that would then give us the prediction on those values on the entire batch. And once that is done, you can compute the loss on the entire batch and then do the back propagation so that you can update the weights based on the loss, and the optimizer will take care of the back propagation and updating of the weights. Once this is done, you can the model is trained over the training dataset. You can then move on to the validation dataset, and in this case you would do a forward pass and compute the loss. We are not going to do a backward pass or the back propagation because we are not training the model in this case, not changing the weights, but we are interested in knowing what the predictions are and comparing those predictions with the true values that we have. So let's begin training a model. We can use the models that are already available in DeepChem or DGL to train it. We'll not create models ourselves in this in this lesson, but we'll look at that in tomorrow's or the next day's lesson. So let's install DeepChem, DGL, DGL Live, RDKit, and FastML. Once it is installed, you will note that it says successfully installed all these packages. We can then move forward with the next part of the code. So it's almost installing. So let's see what we have next. We'll use the QM9 dataset as before, and we'll try to predict the HOMO-LUMO gap for from the smiles input. And let's import the QM9 dataset and load it into a pandas data frame. And once we have that, we can create the smiles. Use the smiles for creating the dataset. And we have the smiles and this gap. Let's say we take a sample of this and take about 10% of the dataset, because it will save us time in training, and this is just a demonstration. So we'll just take about 10% of the data set here. For featureization, we have smiles and gaps. Let's use the fingerprints, and we'll use the fingerprints of size 100. So that will generate us a 100 dimensional vector. And do note the dimension, that's 100. So we need the dimensions for the machine learning model to be 100. So it'll ask us what the dimensions are, and we should put in 100 when we reach at that point. We'll use a radius of 2 and then apply the featureizer to it. Once we do that to the smiles, the thing with the fingerprint that is generated, it's a multi-dimensional array. So we would need to convert it into a list, and the reason for that is the model requires a list-like thing for it to operate. So this function over here uses the dataset fingerprints and then takes the first element of the featureizer, which is a multi-dimensional vector, and this would give you the inner part of the featureizer or the fingerprint. So we'll convert that into a list now, and once we have that, we save it back into the data set. And we don't want smiles anymore, so we just take a subset of the big data set, and now we just use FP, which will be the input, and gap, which will be the output. Once we have done that, we'll just randomly split the dataset. You can use any other splitters for this case, but in this case, what we are trying to do is just randomly do it as a demonstration. So we'll split it with 80% for training, 10% for validation, and 10% for splitting. Once we do that, we'll check whether the thing is splitted right, and we see there's a nice list of fingerprint vectors in here, and this looks good. So we have done the first part where we have featureized it and then split it. If there's some cleaning involved, you make sure that you do it before doing all the featureization and splitting. Make sure you don't have any missing values in the gap or some bad data in your data set. Once we have done the splitting and everything, we will use the data loader. This is the additional step that we need to do in training machine learning models with PyTorch or TensorFlow. The reason being it allows easy handling of the training process. In this, what we are going to do is we'll give the data loader our data set in the form of x and y's, where x is the fingerprint and y is a target value, and which is a float. So once the data loader gets it, it needs to batch it together. Remember that we are not training one sample at a time, because it'll take a long time to do the training. We can't use the entire data set at once because we are limited by the memory. So we have to be somewhere in between a single sample at a time and the entire data set. So that's the reason we are going to use batches. And this collate function that we are going to define over here tells the data loader how we need the x's and y's to be mapped into a batch, because we are going to give it single entries, and this function is going to batch it together so that all the batch can be loaded into the model at once, and the model can try to learn something from the batch. So we have x and y's, and we would provide them as a list in this case, and the x and y's would we have x and y's, we would map them to x and y's, and you will see later how this happens. But once we have those x and y's, we need to stack them, and this is telling how to stack those x and y's, because we have a bunch of these vectors that you see up here on top. So if I'm given these 5 x's as these 5 vectors, how do I need to combine them so that it acts as an input to a machine learning model? In this case, we would say just stack them row wise. So the first row should be the first vector, the second row should be the second vector, and so on. And that's what this is doing. So it is telling, given a bunch of x values, just stack them one below the other. You can also do it column wise if your machine learning model needs columns, but here we need rows, so we say dimension is equal to 0. We do the same for y. And once we know how we are going to batch them, we can create a data loader. Let me run this part of the data set of the code, and this is how you import a data loader. And once we have the data loader, what we are going to do is list, and this would be the x value for us, and the other one is the y value. The reason we are using zip is it creates pairs of x and y's. If you remember, this x train has a list of all x's, and y train has a list of all y's, but we want matched pairs of x and y's so that the machine learning model will take that x to do prediction, and we know what the corresponding y for that is. So this zip function allows us to do that. But we have some more things to do before just passing x into this. We would need to convert the values. So xtrain fp.values would give us an array of values. We'll convert them to a list, and we will pass that list into a tensor. And the reason we pass it to a tensor is all the operations that go on during machine learning training use a tensor to do it. And tensors, you can take the gradients or derivatives and do stuff with that. So we will cast a torch.tensor on the list of all the x values in the trained data set. And this thing is a little bit critical for this part, where we need to specify what type of data we want to create the tensor with. So you can create a tensor with integers if you want, or double, or float, and there's float 32-bit, float 64-bit. By default, the xtrain values that we have here are in 64-bit, and if you don't put in this, the model will complain that the variable types while training are different. So that's the reason we put in this part saying that it's 32-bit float values. And we put in the y values similarly, and let's say our batch size is 64, so we have 64 entries at a time that we are putting it into a model and asking the model to predict. And this is how we are telling the model, the data loader in fact, to stack the entries or create batches for those entries. So once we do that, the code runs quick, and this would give us the first entry in the data set, and we see that it's a bunch of ones and zeros, and this is from our circular fingerprint featureizer, and this is the x value and this is the y value. We see that it's a tensor, and this is also a tensor, and it looks good so far. So we'll repeat the same for the validation and the test data set. We'll put in x valid, y valid, and the same part with fp as the input value, and for the test with batch size 64. You can change the batch sizes anywhere. There's no need of keeping the batch sizes constant. In this case, I've just kept it constant. So now we have the data loader ready to load data into a model. So now let's define a machine learning model. There are ways to create your own machine learning model, but in this case, we are just going to see how to write the code to train a machine learning model and not concentrate on the model itself. We'll do that in lessons that are coming up. So here we'll use this MLP predictor model and try to do the training. So let's run this. So what is this going? This is going to get us a model from DGL Live, and it's going to use the MLP predictor model from there. And this is what the model looks like. We'll discuss what these things are later on, but just to show you, there are some layers in there and some layers and something. This is the activation function that we talked about. So this is one layer, then there's a linear value activation followed by another linear layer. So these linear layers are W1, X1 kind of things, and then you have a value to activate it. So this is just a 2-layer network that we have over here, and we'll define a loss function to compute the loss for training while training, and then we need an optimizer. We'll use the Adam optimizer. There are other optimizers that we can use, but Adam is one of the most commonly used one nowadays. And LR is the learning rate. So remember the alpha that we used to change the weights, and this is the learning rate. Over here I've set it to 0.01. This is usually a small value that people set so that the optimization process is a little bit smoother. So once we execute it, we have the optimizer and everything ready. So let's go over the actual code for training the model. While this is a more elaborate demonstration of what the training code should look like, there are more easy ways to do it, and in that case you would not look at all this code. You'll just put in a model, you'll give it an optimizer and the loss function, and the things go on behind the scene. But in this course I wanted to show you how this thing is done and what goes on behind the scenes as well. But the DeepCam library has just one line of code that does all of this for you, but it's good to know what goes on behind the scene. What we are going to do over here is go over the dataset 5 times. So epochs is equal to 5. We are going to loop over the epoch. So in this part, we'll first try the training part of it. So we'll do model.train. So we'll let the model know that we are training, and you can change the weights, the W1s and W2s now. We'll have a placeholder for training loss so that we can compute. We can just save the loss over each batch and then at the end of all of the batches, we can estimate what the training loss over the entire data set is, or the entire training data set in to be particular. So we have the train data loader. From train data loader, we are going to get a batch. So every time it's going to give us 64 entries from the trained data loader. And those entries, as we know before, have X and Y's. And this comes from the top function that we used. So the collate, it gives us X and Y's. And depending on what you give here, that's what you're going to get out from the batch. And we know X are the fingerprints and Y is the target value. So we'll go down there, and we'll say X is the features, or this is the features, the X, and Y was the target. So the model over here needs the features to work on, that's the input. So we'll say prediction is equal to this features. Once we get the predictions, we'll compute the loss. And remember, we already created this loss function. So we give it the prediction values and the target values. Target is the actual value, and take the mean of that, because this is over 64 entries at once, remember. Because we have a batch size of 64, so there'll be 64 losses, and we'll just take a mean of those losses for one batch. And then initialize the optimizer. And once we initialize it, we'll do back propagation. So loss.backward will do the back propagation for us and compute the derivatives, and the optimizer.step will do the updating of weights and everything. Once this is done, we can save the loss for one batch and move on to the next batch for doing the same thing. And once it's exiting the loop, it's going to take the mean of all the batch losses and say this is the loss on training. For validation part, once all the training data is passed through the model once, we can say, okay, let's look at the validation now, validation data set. Over here, it's important to note that we are using model.eval instead of model.train, which was for training. So we are evaluating it. This lets the PyTorch know, okay, now I should not change the model weights while something is going on here. And we'll use valid loss is equal to a placeholder of list, because we just want to do something like this, where we compute the loss over all batches in the validation dataset. With torch.noGrad, this helps to avoid computation of gradients and speed up the estimation of results. So we just use torch with noGrad for the evaluation part. If you are using the test dataset, I would recommend doing the same. And this part of the code is similar to the training, but we are not going loss.backward. There's no back propagation, so we'll do a forward pass and then just compute a loss and take the mean of loss. This model is not a great model, but we should see some improvement in the predictions that we start with. So we see the first time it went to the dataset, the loss was 0.04, and the next time it went to 0.006. And we see some improvement over here in terms of what the prediction is going on for the training loss as well as the validation loss. We see some decrease in validation loss. So the number of epochs depends on you. You can run it for as many epochs, and you can stop it when you see that maybe the validation loss is not improving, maybe after 5 epochs. So if you put in 20 epochs and at 10 epochs you get 1 validation loss, and after 15 epochs the validation loss is not changing, you can wait for another 5 more or 10 more epochs or something like that, and then maybe just stop it. And once you stop your training, you can do the prediction. Say we want to look at some entry in the dataset, and that's 159th entry. And we have the x value, which is we get the from the index 159 from there, and the corresponding y value. So this is the homo lumo gap for this entry. So what we can do is we can pass it through the model, and we can use model.predict, and there's no need of even this predict part of it. So we can just say model and pass the model dot torch. Remember, we need to pass in the same input as we give it to the model. So in the test, in the loader, we remember we had done torch.tensor and then passed in a list of samples. So we need to do the same thing over here, and once we do that, it'll give us an output. You see that the model prediction is not so good, but this model is not intended to give us good prediction. If you need good prediction, you need a more complex model and also train it for a long number of epochs. In general, people who report machine learning models sometimes train it for days or weeks to get better results, and this is a just demonstration, so we don't expect good results from here. Once we see that it's giving us some values, it was training, we can look at the prediction values and make a plot of it. So in this code, what I'm trying to do is get a list of all the true values, the target values, and do prediction on all those values. So we have the test data set, we convert into a list, and that will give us a sample similar to above. And we can still use this code, which is model.torch, and then we pass in one sample at a time and do the prediction, and we get one prediction just like this one above, but we are appending it to this list of predicted values, and we'll get a list of all predicted values. So once we run it, it's successfully run, and we can compute something called R2 score for this. And as you see, it's not so good, but once you have the true values and the predicted values, you can do this on the test dataset or validation dataset and compute the R2 score of Pearson coefficient, which tells us how correlated are the true values and the predicted values. In this case, it says it's not so correlated. That is expected because we didn't train the model for long, and the model itself is not so good. And if you have reached this far, this is a great way to get started with training machine learning models with artificial neural network architecture. I hope to see you soon in next lessons.